Hallo.
I'm Sophie Kroon. Nice to meet you. Nice to meet you.
Hallo.
Hello.
Eerst waar ik sta is verplaatst.
Benjamin, sure. You can have a seat there. Here's still a student. Here's still one chair available.
I think this one was I know that one or this one. Maybe take this one. Yeah.
Benjamin, some coffee, tea, soft drink.
Good. Good to see you again.
Good to see you.
Oh yes, coffee will be great.
Yeah. Always.
Ja, dan kan ik misschien al de helft van de presentatie en dan hier staan.
Milk and sugar?
Yes. Fine.
Okay. Help yourself with some biscuits. I think this is this on the vegetarian? Is it with carrot? Is it a carrot one?
I didn't try it yet.
Huh? Help yourself. Yeah.
Dus iedereen zegt, de belangrijke mensen moeten zich
Nou ja, ik denk het omdat je er op staan maar is het niet. Dat is dan niet.
Okay, so let's start. Thank you very much, Benjamin, for being here, and thank you very much for taking the time for supervising Thomas. Thomas, you have 20 to 25 minutes for your presentation, and then we will make some questions to your work. Okay?
Yes.
So whenever you want, you can start.
Yeah.
Maybe one comment, just to say Rowan was supervising Thomas, also made a lot of work, but he couldn't be here because he's working for another division. So I'm here for both of us, and it's only normal that we support Thomas. He was very present and supportive, so I'm really looking forward to hear his presentation. And thank you for this kind of warm welcome. It's very nice.
Thank you very much.
Okay, so I'm Thomas Simmons, and I will present my master thesis topic, which is automated toolchain to create wide-scale RDU routes and simulate emission distribution across EU roads. It's a pretty long name, but I'll explain down the line. So this is the table of content which we'll discuss. So the background, the methodology, the results, the conclusion, and future work. I'll start with the background. So in the last decades, air quality and air pollution has gained a lot of attention and is seen, or in several studies, is seen as a global threat, having a large impact on human health and ecosystems, with actually several European cities still exceeding limits. The effects are on human health and ecosystems. So on human health, it has cardiovascular and respiratory diseases, cancer, and in studies it shows that it's associated with high death rates. For ecosystems, it's global warming, acid rain, depletion of ozone layer, so not much good coming out of the air pollution. One of a big contributor to these harmful emissions is the transport sector, the road transport sector, with 28% of NOx and 6% of PM coming from exhaust of vehicles, of conventional internal combustion engines. To tackle this, or in response of this, authorities have put emission regulations, so limits on these emissions. Car manufacturers are driving to actually increase or make the air quality better and make human health better by studying or applying electrification, so hybrids, fuel cell vehicles, and also, of course, after treatment and general engine technology is ever improving. So regarding the emission regulations, so to reduce pollutants coming from the road transport, authorities are trying to reduce these pollutants by imposing regulations. So over the last decade, it started in 1970, these regulations have been accelerating and have been becoming more and more complex. Before 2017, everything was tested on a chassis dynamometer. So all patterns were static patterns that were tested on the chassis dynamometer where the emissions were evaluated. But these chassis dynamometers have a lot of limitations, which is shown in the last years. On-road conditions are not the same. So if you drive on road, you have a lot of conditions such as road grades, weather, which stress the system more. And also in the last few years, there were some issues regarding defeat devices, such as seen in the case with Volkswagen, where the chassis dynamometer testing is bypassed to create less emissions than actually performing on road. And of course, due to the on-road conditions, the engine operation area is a lot more stressing the system, as I said. So due to these chassis dynamo limitations, the European Commission has implemented a fully new testing methodology called real driving emissions, RDE, which is actually complementary with the current testing methodology and is completely performed on road. So this is just a general pattern overview. A normal RDE route is driven on road, is between 90 and 120 minutes, and is separated in 3 driving parts with the same share. So you have urban going to 60, 60 and 90 is rural, and then over you have motorway. This is very wide term, so there's a lot of regulations regarding these real driving emissions to frame or actually create boundaries so you can not just drive on the road for emission testing and do whatever you want. So there's 3 main regulations, one regarding trip conditions. So there's a lot of limits regarding altitude, temperature, max speed, a lot of regulations which can be found at the European Commission. And then you have trip dynamics to ensure normal driving behavior, so to avoid excessive acceleration or very mild acceleration, there are also some limitations. And also to compare, to make sure that, for example, not extra weight is put on, there is a comparability of CO2 with WLTC. And then, of course, normally the chassis dynamometer is all done in the inside. So for the RDE, there is a portable emission measurement system put in the car, which records the pollutants, the GPS signal, and onboard diagnostic signals. So what does this bring, this RDE? Actually, due to the transition to real driving emissions, previously the emission testing was clearly defined. There was one testing pattern. Every OEM knew exactly what the pattern was. But now with real driving emissions, actually the spectrum enlarged and the complexity became a lot bigger due to all these on-road conditions. So two main problems were proposed or had to be tackled. So there's no possibility of repeating the same RDE test twice because it can be done over whole of Europe, and every variable acts on the same time: traffic, ambient condition, also driving style is very important. And actually the combination of these parameters, it's uncertain to know which conditions or which combination of conditions stresses the system, the powertrain and the emissions the most. And then the second part is the testing environment. Because it's all over Europe, displacement and also the expensive equipment you have to bring can lead to high logistic costs, and also on-road testing exposes people and the expensive equipment, which can affect safety and confidentiality. To tackle this problem, Toyota wants to actually fully grasp Toyota customer behavior and on-road driving conditions across Europe and evaluate emissions and how customers are driving in Europe. So a simulation tool chain should be made to statistically represent real driving emissions in Europe. So the target setting or the end result should be a tool chain that generates real driving emission compliant routes, so with all the regulation involved, and should represent customer behavior, so coming from actual data. As it should be a good distribution and a very large data set, there should be a good accuracy between, or a good trade-off between accuracy and processing time. And of course, adaptability to have different tools implemented and maybe change vehicle models. Should be a very versatile tool chain to create sort of a repeatability in testing, so you can repeat certain tests with a narrow band of parameters. So this is an initial image of how the tool chain look like. You have the route generation, which generates a lot of RDE routes. There should be a driving behavior implemented, so different accelerations. From that driving or from those speed profiles, there should be a power model created for both vehicle power, engine model, so all the power and force calculations. Then the route validation should be done, so the RDE regulation should separate for void or valid routes, and then emissions should be calculated and put into a nice visualization to be used across divisions. So I'll start with the first one, which is actually a very small part because it was already existing. So it is the route generated, RDE routes, use a graphical information system. It can create a high number of RDE regulated speed profiles across Europe. So it's an external program that is used to recreate a very big amount, a large amount of RDE routes, which gives speed profiles, slope, and so on. Then from there on, a driving behavior should be implemented. So firstly, which was done by a colleague, was the acceleration intensity, which is if you see one speed profile, everyone can drive it differently. For example, Tom can actually accelerate like a madman, while maybe Ravindra is a very smooth guy who accelerates very slowly. So this is done by a colleague of mine. And then I did the acceleration patterns, which is for the same speed profile, for the same acceleration, the same energy balance. Someone can put the axle pedal in one smooth go, or also actuate the pedal multiple times, which creates a different engine on and also different emissions. So I had to model this and recreate onto the toolchain. So I'll quickly explain the model concept. So the data used was actual data, so it was over 2,000 trips or 3,000 trips with no common conditions. I extracted all the accelerations. So if you see, the speed is the same, but the power or the axle pedal demand is completely different from person to person. I extracted the pure pedal disturbance from every event by using a sort of a perfect acceleration, and then the deviation from that perfect acceleration would be a pure disturbance from the driver itself. But because there was no common conditions, so road grade, power demand, nothing was comparable, I made it comparable by using frequency analysis to actually extract the time-based signal and just purely look on the frequency and amplitude on how someone uses the acceleration pedal. And from there, I use a sort of a clustering method to recreate disturbance profiles. So a different range in severity of disturbance, acceleration pedal disturbance. Then next up is the vehicle model. So with a speed profile and slope, you can actually calculate the vehicle power, which is done on the general vehicle dynamics formula based on road load, speed, acceleration, which we learned from Gregory 2 years ago. Then the engine power model is actually something I got from logic study inside TME, Toyota. So there was a very, very basic model which just uses the same engine power as the vehicle speed model, and there was actually no battery model included, which caused a lot of gaps. So this is before countermeasure. You have special conditions such as a different engine warm-up, a lot of engine starts missing, and the power values were not the same, which also led to different coolant temperature, which is a huge gap, especially, for example, if you want to calculate PM, temperature is very important. So to tackle this, I actually implemented a battery model because both the engine start-stop threshold and actually the power itself is dependent on SOC. So when the SOC is very low, the battery or the engine provides extra power to actually charge the battery and vice versa. And the same with the threshold. So when the battery is low, actually the engine power or the engine start will, the threshold will be lower, having more engine starts and more charging of the battery. So including this SOC model, state of charge model, based on a gray box of statistical data I got from actual routes and logic study, I got these results. So it's an improvement, and also on the engine coolant model, there is improvement. There's still some room, some small gaps which can always be tackled through a more logic study. Then next up, if you have all these routes, all these powers, you should separate them. So for based on RD regulation, one was the trip dynamics, so acceleration-wise. Every route is validated in terms of acceleration. Very high accelerations are limited, such as by VA pause, which is to make it not too aggressive, and also low accelerations are limited to RPA. Then the second one is CO2 normality, as CO2 is seen as sort of the metric of vehicle dynamics and like wind, payload, road rate. It should be comparable with WLTC. You cannot drive in certain conditions where the CO2 or the dynamics are too high or too low, so it should be comparable with WLTC. So there's a sort of regulation having windowing, average windowing, to ensure it's actually in the band of WLTC values. Then the last step of the toolchain, or the second to last, is the calculation of emissions. So for this emission model, the ECU map inside the vehicle was used. So in every Toyota equipment at GPF, there is an ECU map to predict and prevent gasoline particulate filter clogging. So it prevents, or it predicts when the enrichment should happen to prevent this. And it's based on the engine load, engine speed, and coolant temperature, which I extract from the model. And the result should be a bell curve with all the routes, where you can see which routes are more severe and less severe across full Europe, so actually represents customer RD emissions. And then last step, with all this data, there should be a nice visualization. So from all the outputs I can get the engine starts, vehicle stops, slope, traffic lights, all those KPIs or parameters that are important for emissions or affect emissions. I can actually store into a database and show to a clear visualization based on geographical traits, comparison, so statistical comparison of these regions, and also in-depth analysis of specific routes. So the results for disturbance, this is the end result. So if you see from the full toolchain perspective, from the same vehicle speeds profile, you can actually create different vehicle power demands due to an axle pedal representing customer data, different engine power because there's multiple engine starts due to different vehicle power, and of course also different emissions. I validated this firstly through an easy visual validation to see if the magnitude and the fluctuation was similar, and then of course through a statistical validation by comparing parameters affected by the disturbance. and if they were comparable between simulated and actual events, such as engine starts or emissions. The engine power model was improved and actually showed a good correlation between simulated and actual. And of course, like I told you, there's always room for improvement, but this is always a trade-off between accuracy and processing time. So the more you go into the logic study and the more you recreate the logic, the less the processing time is, or like the worse the processing time is. The emission validation was done by evaluating different patterns that were driven on the chassis dynamometer, and by simulated PN and actual PN, we could see a trend. But of course, more data would be required to have like a complete image. And then, of course, the processing time, the initial status of like the separate tool was around 9 seconds for only one driving style, which took, if you take 1 million routes, 202 days. And my tool, or the new status, so by reducing the processing time, was around 5 seconds, which is 50 days. So if you have the initial status with different driving styles, it can go up to 400, 600 days to process the full data set in Europe. So my conclusion is just a quick conclusion on what I actually achieved. So from the target setting, I achieved a fully functioning toolchain, which can give RD compliant routes based on trip composition, trip dynamics, CO2 normalization. And using actual big data, we can represent actual customers. The accuracy and processing time was good. And through modular programming, actually, the maps could be changed for different vehicles, and implementation of other tools were easy to implement. And then using this simulation method, repeatable RD patterns were created, which operate in a specific condition. So there was a sort of a repeatable environment that was created. And then, of course, future work is mostly continuous improvement and validation of the tool and the visualization. So using backward and forward validation, gaps in the current tools can be defined and improved. So using simulated routes coming from the toolchain and recreating them on the chassis dyno can show the gaps of the tool. You can improve, and this is like a continuous process. Then secondly is a reevaluation of current emission test cycles. Because RD is so wide, every emission can have a different stress of the system. So for every emission, a sort of bell curve can be created to reevaluate which patterns are more severe for every emission. And then actually, I would like to end with an end note. So I think like the full technical process is one aspect of the thesis, but also through like the year of working at TME and also working for the consortium, actually also like a personal development was made. So working with the people at Toyota, I had learned a lot about self-reflection, actually looking at my job and actually be proud of it, but also making sure that I can develop and challenge the results I got. And also effort and problem solving, you should go beyond what is asked and try to grasp and put extra effort in and think outside the box to actually do more than is asked. And of course, they gave me a lot of structure and also a lot of base for my future time. And teamwork is the most important. So I would like to thank everyone involved with this, the students, consortium, and the colleagues at TME, my manager.
Thank you very much. Thank you very much for your presentation. If you don't mind, I will start with some questions.
Yes.
And then I will give the floor to the rest of the table. First of all, I want to give you congrats, to congratulate you for your work, for the work done. I think it's a really nice presentation, a lot of content, a lot of different aspects to be presented, and you've done a really nice presentation, clear, precise, good shape, and I like what I read on the report, and I like what I've seen in the presentation. I have several comments and several questions, and I would like you to go to slide 8. Yeah, you said regarding how to understand right the
Yeah.
behavior and how to extract
Yeah.
the pedal disturbance. Have you how you have extract precisely that disturbance? Have you what you've done? Have you take some GPS signal estimate which will be the maximum acceleration and then extract from them
That's why I
the perfect just because you said related to the perfect pedal shape.
mhm. Yeah, so I had for the perfect pedal shape, actually took sort of a few pointers or a few a frame to work on. So I wanted the first initial actuation of the vehicle or the driver should be anyways the first slope of the smooth intention. And then I made like with a second degree polynomial, I made the most smooth possible power demand with the same actually energy balance. So it was a bit of an iteration, so sort of the best fit uh, to have the same slope in the beginning, but also having the same energy balance. And yeah, like it's sort of the best fit between the min and max.
Because here, and then I have a second question regarding the frequency analysis, but here I think it's the data you're showing can be really affected by this decision in the sense that maybe you can try to estimate maximum acceleration, minimum acceleration.
Yeah.
Whatever the decisions you take here, it will greatly affect the results you will show you. But then you obtain that theoretical perfect acceleration curve, you extract the variation, and then you perform a frequency analysis on that variation.
Yeah.
And that's the data you've used for.
So it was the problem about this project was mostly the common conditions. So it was actually data from different drivers, different accelerations. So I had to tackle it differently to actually get comparable data or even, because everything was different. So.
And I guess the higher the correction frequency, the higher the emissions, or not?
Yeah, so it's dependent on the magnitude and the fluctuation. So higher load, which is the amplitude, and higher frequency, which is sort of the engine starts, means more severity in.
And I have another question in slide 10. You said you have limited high acceleration rates.
Yeah.
And which is again the criteria you've used for decided what is too much acceleration.
Yeah, this maybe I didn't explain, but this is actually in the regulation. So this is an actual line in the regulation that says with a calculation that says take for every part, so urban, rural, and motorway, take all the accelerations, order it, and actually remove the top part and the highest acceleration. So for every of these, there's actually a clear regulation.
Some kind of Gaussian analysis, just removing the limits.
Yeah, exactly.
Good. And my last question, it's slide 13. Here, related to the engine power, I have a doubt, and it's you're showing an R2 of 82 and 90, which is really good.
Yeah.
But do you really think it's a linear regression between the engine power and the engine?
Yeah, so actually I should have put, for example, the RMSE for the engine power, you mean? Like it could be a linear difference from the.
I guess it's some kind of polynomial or some kind of logarithmic relationship. Even.
Between the actual and the.
You have a line, you have a straight line. The equation is a line.
Mm-hmm.
I guess that the relation is more an exponential or a logarithm.
Their relation should be a 1-by-1 correlation because it should exactly match actually. So this is like the actual engine power, and then onto the the simulated engine power.
Okay, no, I did understood something different. Okay, good. Okay, and honestly, thank you very much for your presentation. I think it's really, really good work, really good presented. And last thing you need to learn from this year is how to properly iron.
I tried this morning, but while going here, actually,
Apart from that,
yeah, I know. I ironed, but it wasn't good enough apparently.
apart from that, congratulations for the work done because it's really professional analysis and it's outstanding
Yeah, thank you.
presentation. So thank you very much. I give the floor to you.
We'll take note for the ironing for the next interview. We'll include that.
It's me?
Yes.
Okay, so thanks a lot for this presentation. First, because I read also the report, I would say that the presentation for me it's more clear than the report because in particular at the beginning of the presentation you present the global chain, which was not completely presented in the report, and for me it gave me the life cycle of your work in fact, and so it's very interesting, and also because the presentation is very clear for everybody, so it's very interesting. I have very few questions. My first question is concerning this one. You said, okay, I measure some emissions, but I did not understand which kind of emission because you can measure several kinds of emissions, CO2, NOx, and so on. So which kind of emission do you measure?
So several emission models were created, but currently the one I used was regarding PN. So as I said, PN was actually already in the vehicle ECU map. There was an ECU map which actually could simulate PN already. So I implemented the vehicle ECU map into my tool. So the other models, emission models such as NOx or CO, are actually still ongoing or still ongoing.
Okay. And concerning the comparison, the validation, the comparison with real emissions, because I did not exactly in the visual validation, I did not see exactly how you can say that you are not so far from the real emissions.
Yeah, maybe this is a bit of an abstract way of showing the data, but to actually, this was the first thing I did was just I have a result. I want to see, does it even resemble? Because if I don't put it on top of each other, I don't really know, like I said, the magnitude or the fluctuation. So I compared all, or not all, because that would be a very time-consuming project, but just visually compare different accelerations just to have an initial image. The actual validation is actually the statistical validation.
Okay. And at the end, the objective is to allow the company to have a first simulation before to go to the road, or is it to have something that could be validated by European Commission to say, okay, if the result is good in your chain, then you have 50% of chance that, or 80% of chance that at the end this will be validated by the European Commission.
I think this is something that will be used inside the Toyota Corporation.
But there is no objective to have something which is validated and.
Question to him.
Oh,
that's good. You should stress because he needs to know what he can say and what he cannot say.
okay.
Okay.
So now, because this is interesting to have a process that at the end is validated by the EU or validated by an organism, something that could be transferred to maybe to another company or to another, and to say, okay, if you can demonstrate before to go to a road that 80% of your parameters are correct, it's a huge save of money and time.
I think this is a possibility. This can go any direction actually with the tool. So I think it will be first be evaluated inside TME for Toyota to be then.
If I can add, because this is, at least I'm entitled to say that, probably he's being very cautious, and I appreciate that. This kind of tool, basically our process, how we develop, is not something that, how can I say, we want to hide or we want to, let's say, make a mystery, but it also includes some kind of knowledge. So we have to find, with the authorities, we have to find the right balance between explaining what we do and also protecting our competitive investments. So if we have to, for example, disclose everything to the authorities and then I'm a BMW and I just sit in the room and I learn everything you know, that's also not very good for innovation and let's say a good business environment. Then the second point is if we are discussing with authorities, either proactive or reactive to some issues, this can be one of the tools to explain, okay, this is our philosophy, this is how we have developed, this is how we have embedded the development of all the conditions and beyond to satisfy the regulation and consider all of the customers. Then to achieve something that can be as trusted as a, I would say, an on-road test for all the conditions and computing that in 4.5 seconds for a route of 90 minutes. If we can do that, then I think it will have far, I'd say, much more bigger implications than just validation. So this is just the first step. We have many ideas.
Okay. Thank you.
Thank you very much. Maybe you want to make some questions.
Well, maybe one question I have is if you could have more time or if you could have gone faster, what would you have liked to do extra to what you showed here?
Like I said, I think it's mostly firstly continuous improvement of the engine model,
Uh-huh.
but also maybe this is a tough one actually.
I never spared you, so
What should I have done extra, like go beyond? Yeah, I think it's mostly the continuous improvement for me. Like the engine model, everything is still very robust and very rough. So I think there's always room for improving the tool just in general.
okay.
Thank you very much.
I have no questions. I really like the presentation.
I have one question. You use frequency analysis to validate or to compare model outcomes. Only in the driver behavior, or have you used it somewhere else as well?
Currently only in the driver behavior.
And why is it that it is very well suited to validate the driver behavior?
So like so one slide. Because it didn't have common conditions, it was the best possibility to actually show how someone actuates the pedal. So I think for this one, it also like it was not spot on the first route I took. There were a lot of dead ends. So this would, for the driver analysis, was the best option to use.
And where can you possibly use the frequency analysis in other steps, or haven't you considered it, or if you should consider it?
I think in other steps, mostly these steps are mostly based on logic study. So if there would be an extra step such as a different kind of driving behavior or something external, it would be useful. But for the vehicle model, emission estimation, it's actually mostly logic study and trying to recreate like statistical data and create statistical maps of the vehicle. So it's not really in use for those steps.
So thank you very much for your presentation. And if you give us 5 minutes for the
Yes.
evaluation.
Do I stay?
Yes. We need
No,
your, we need your,
No, I
we
don't
need-
want to be in the way of the process.
yeah, but So, okay, so congratulations, you have passed the defense. You have to iron again.
Yes, I know. I will.
Sure. And yeah.
Iron.
Yeah.
Yeah.
Hello, are you?
I just
Fine.
take it over there.
Hello, how are you? So congratulations.
Thank you.
Pretty good work. And,
And you will not have your grades now, but you need at the end to have the jury and so on.
It's good. Well, thank you.
Also, congratulations from my side. Good presentation, clear. Thank you. You did a good job in sharing the topic with the right level of, I would say, expliciting, but also keeping the confidentiality that we requested from you. This is very important. So thank you for that.
Thanks. You helped me as well. So.
I will go back to duty anyway, but enjoy the rest of the presentation.
Thank you.
There you are. Bye-bye.
Maybe it's a little bit impossible. No. Well, I'm staying on this chair. See you tomorrow. See you.
David here?
Send me a thumbs up. I don't know. It's our face. David is
David is
connected.
watching.
You send me a text.
But he can hear us. Hello, David, can you hear us?
But he's not.
Maybe there's not a call with anyone. He's just watching, but he cannot say anything. So you should.
Yeah, I see you. He's just.
Okay. Okay.
Okay.
Good. Hello.
So
you can't replace this here.
No.
no, but we should call him.
Okay.
Later.
Yes.
So, okay, so thank you very much. As your colleagues, you have 25 minutes for your presentation, and then we will go for the questions. So, whenever you want, you can start.
Hello, my name is Thomas Bokstade. Welcome to my master thesis presentation for the joint master degree in sustainable automotive engineering. The subject of this presentation is the influence of reflectance on range and accuracy of the Quanergy M8 lidar sensor. My academic supervisor is Professor Yves Duck from the University of Groningen, and my industrial supervisor is Professor Dr. David Blackman from Cal State LA. I'm going to start with a little overview on what to expect out of this presentation. First, I'll talk about Cal State LA. Then I give a short introduction on autonomous driving because I think you're a knowledgeable audience. Following that, I'm gonna dive into what sensors in automotive are being used, and more specifically, the approaches to LiDAR. LiDAR means light detection and ranging. Following that, my research, the motivation behind it, the methodology, results, and the conclusions with proposals for future work. And in the end, I would like an open discussion with the room about where we are now in autonomous driving and what we can expect from the near future. First, Cal State LA, that's California State University, Los Angeles. That's where I did my internship and my thesis. Cal State LA, and California in general, actually, has a heart towards sustainability, and they really want to be a market leader in that for students to advance in vehicle technology. That's how I acquired the Quanergy sensor. It was a sensor they bought the year before, little research. And there was even some small startups around fuel cell vehicles. I think there were like approximately 15 or 20 fuel cell vehicles. It was TEC 4760 on measurement, instrumentation, and control. So I gave a lecture about the same topic I'm going to lecture you about, and a short laboratory session with the LiDAR sensor you see mounted here on the tripod. The short introduction to autonomous driving. This is something we probably have all seen. It's the levels of autonomous driving. And the thing I want to talk about is, these levels actually don't say anything about the technology behind it. So from a technological point of view, if we just look at steering and acceleration, what the system does, it takes in information from its sensors, it processes it, it perceives the environment, it makes a decision, it actuates its control algorithms to eventually put the steering wheel in an angle and put the throttle and the brake. On this level, the system is, the computer is always in control. It's only from this level when we are monitoring the driving environment or the fallback systems that there's a difference. This is important for when the computer is driving. In a level 2 system, the human is always in control. So if I crash a Tesla while I'm in like self-driving mode, I will be responsible. If I'm in a car that doesn't even have a steering wheel, I can be held responsible. So it's important for lawmakers. From a technological point of view, there's no inherent difference. I mentioned Tesla and Waymo because I believe those two companies are the front runners in their respective strategy towards self-driving. In the future, I wouldn't want to talk about level 2 and level 4, but actually a vision-based system versus a light you can use. You have camera, which is vision like our eyes. You have ultrasonic, which uses sound and is for a very short distance. These 3 sensors are used by Tesla. So they use 12 ultrasonic, 8 cameras, and a frontward-facing radar. Companies like Waymo contrast. And so it's great that traffic sign recognition, a car, that's all what it's very strong at. It's not that great in the dark or in really rainy, foggy, or snowy conditions. But it resembles our human vision. If we drive a car, we use practically the same sensor as a camera does. Ultrasonic, as the name implies, if it beeps, that's an application for ultrasonic sensors. It's just a very specialized sensor. So it's great at what it does. It's not great in anything else. We have radar, radio detection and ranging, and very similar. So it's also cheap and very small to integrate in your vehicle. And you see it in practically all the newest vehicles. For example, for adaptive is quite limited. Because it uses radio waves, it's a really big electromagnetic wave instead of visible light is a very short wavelength. It can see around the humidity, so it can see around water droplets. And that's why it's great for redundancy for those kind of applications. Then we have thermal sensors. They operate in the infrared spectrum and are great at heat detection, which is very interesting to see warm-blooded creatures because those are the things you want to avoid. If you build an autonomous driving application, you don't want to hit people, you don't want to also hit dogs or something similar. It is pretty good in all weather conditions. It uses a longer wavelength than, for example, vehicle as a little bit of a gimmick. And then finally, LiDAR. LiDAR, as said before, light detection and ranging, is extremely accurate in depth perception at higher resolution than radar, but also struggles in humidity. So it uses a wavelength very close to the visible spectrum, but that's why it also struggles in the same conditions as the visible spectrum struggles. So in snow, fog, rain, that's hard for a LiDAR detection. You can also, you can see the point cloud, so it's always measures that later. But most importantly, right now, cost and size. LiDAR sensors are pretty bulky and are extremely expensive. The sensor I worked with was, I believe, around $7,000 when they first bought it, and it's quite limited in their in the specifications. There are many different approaches to LiDAR. How does it actually work? So light detection and ranging, it's a time of flight sensor. So the LiDAR, it sends out a laser pulse, it bounces off yeah, so there are many different approaches to LiDAR, depending on the application you need. The sensor we're going to talk about today is the macromechanical scanning one. But there are also a lot of different approaches. The macromechanical scanning LiDARs, spinning LiDAR systems you often see on test vehicles. They come from the DARPA Urban Challenge, for example, because that's what they use then. But because they know it's very expensive, they try to work on other things. Solid state LiDAR, a micro electromechanical system, or an optical phase array, which is a different product from Quanergy, or flash LiDAR. The Belgian company Xenomatics does that, and that's application, or automotive application in general. Okay, then I would like to go over to my research specifically and the motivation behind it. I gave up some specs of the Quanergy M8 sensor, and when I first got it working, I tried to look at it with my camera. So this is the sensor on with the computing environment. If I would look at it with my naked eye, I wouldn't see it because the wavelength is 905 nanometers. The human spectrum is somewhere between. I see it with the camera in my phone. 905 nanometers is very close to the visible spectrum. And that's why you can't use a super powerful laser pulse because it still needs to be eye safe. There are different LiDAR approaches. For example, one of the things I showed before. There are also LiDAR sensors with a wavelength of 1550 nanometers, which is far away from the visible spectrum. And then you can use more powerful lasers. Using a more powerful laser will give you more maximum range. So for example, Luminar use more power requirement for your laser. We have the frame rate and the angular resolution. So this is a spinning LiDAR system. You can, in your software, you can choose how fast you want to spin. So if you want to spin at 20 hertz, you will have a more frequent update of your environment, but your angular resolution is gonna be a little bit more. You can spin slower, but then you have a better angular resolution. These angles are very, very small, so I don't think the difference is that important. Other mechanical scanning systems, they don't spin, and they can play with their frame rate and the detection layers. So the sensor I have, you see here, I'll play this video again. Those are actually 8 lasers with 8 detectors on top of each other. So you have 8 layers that you can measure with in between always like an angle of 3 degrees. That means, once you go farther away, those 3 degrees become way too much actually. The top end lasers, the top end sensors use at least 64 and even 128 detection layers. Okay. Voilà. As you saw before, sorry, the maximum range of 150 meters is based on 80% reflectivity. The pulse you send out, it reflects off an object. That is at least equally as important to your measurement as how powerful your laser is or how many layers you have or something. So that was something I wanted to investigate. Like, what if I take a lower reflective object? How far will the sensor be able to see? If I take, for example, only that's something that's like 10% reflective, will I still be to see 150 meters or will it be 100 meters or something like that? In an intensity value. That intensity value is based on how intense your laser pulse is that comes back. In the raw data here, it's visualized through a color. So a blue color will be higher reflective, a green or a red color will be lower reflective. Okay, I started with my work and I had a bit of a do-it-yourself approach. I selected some material panels that I could find and could make myself. So for example, I have a really black flat paint that's about 2 or 3% reflective according to their spec sheet. I just had some cardboard, I used some silver paint, and I even used the metal surface because yeah, something can reflect straight off it, but something can also reflect and scatter in the specific wavelength you want to measure. So for me, it would be 905 nanometers. I didn't have that yeah, equipment available for my research, so I used this can be improved on, but as a proof of concept, I think it works. This was my testing ground at Cal State LA. I had the parking. But first of all, I looked a bit at the research, what has been done before, and I found a previous research of the same sensor, but a previous version of it. So you can see it's still the quantity and gauge sensor, but yeah, let's say a version 1 of it. And there was some research about it, so I wanted to compare, okay, did they improve their product over time? And then, yeah, okay, the thing we see, the first is a temporal stability test. The thing I did was I let the sensor cool off overnight, and then in the morning, I plugged it in, started up, and immediately started measuring just a wall. I put it here, I'm measuring that wall, and let it just measure for an hour, see what it does. In the is between just below 10.5 to 10.54, so about a 5 centimeter spread. Yeah, that tells me that they definitely made improvements, especially yeah, especially when heating up. I did this in California. I did an indoors test. It's pretty mild, temperature-wise. I can imagine that if I would have if I would have the sensor on a car and somewhere in winter it's -5 degrees outside, that this slope will even go farther down because the sensor needs to heat up. I could also see the temperature of the sensor, which would after an hour it would reach approximately like 45 degrees Celsius. So it would heat up between here and here 20 or 25 degrees. The same thing is the quantization effect. Sooner or later, your sensor is going to have to decide in what bracket it's going to put its measurement. In the previous version, it did that with intervals of about half a centimeter. So between here and here, you always have like a half a centimeter. In my research, I noticed that it would be. I wanted to mainly look at the influence of the reflectivity of the materials. So as stated before, I selected some materials and then tested them. First, I did like a static test. So I just placed my sensor here, I placed my measuring board over there, and then I took 100 data points and then plotted them over time. And then over time, I noticed that a very high reflective panel would have a very narrow spread and a high histogram, while my lowest reflective object would have my 8 meters measurement. But here you can say the same thing. You can see the lasers measuring that object, comes back, and then I plot it over time. I did this for, I believe, 7 distances for 5 different colors, and I wanted to plot them all in the same thing. So this is actually one overview with all the data in there. On the x-axis you have the distance. So these are my 1.5 meter measurements up until 50 meter measurements, and then the size accurate my measurement was. So in the previous slide you saw a very broad and a very narrow. It's about 25 meters, so it's actually this blue button, this blue ball, and the green one. So those are the 2 measurements we saw in the previous plot, but then now for all of them. When I went past 30 meters, I couldn't make accurate measurements anymore. I couldn't see it. I wasn't confident, and that had a lot of reasons. Initially, I was planning on making measurements at 75 and 100 and 125 and 150 meters, but I couldn't be confident in my thing I made myself. Because if I would put my sensor, let's say, on top of a car, it would be at 2 meters height, but you only have 8 lasers. And between every laser, there's a 3 degrees angle. As soon as I angle my laser a little bit down or a little bit up, I'm not going to be able to see once I hit 100 meters, for example. So on the sensor, and it levels it out to approximately 0.1 degree. So I could level all my sensor out approximately here, but that was like a millimeter that I had to shift up or down. And then even still, yeah, I didn't know if I like as soon as we hit more than 7 meters, you see that the spread is already half or even a meter. That's that short distances. That's not a great resolution. Hence, yeah, I was thinking like, how am I gonna actually investigate the maximum range, because it's not gonna be easy to look at it. I put my panel on the little card and I try to roll it forwards. You see it's very uncertain. The thing we see on the side is the reflective bands. But then for very long measurements, so that was for my low reflective object, was less than 10%, that had about 30 meters of range. But for very long measurements, it was very hard to actually do a measurement. That's why I wanted to pick a real life object, and I used the campus bus. I did the same thing, and then from here, from here on out, you can kind of see that you don't see everything of the bus anymore. It might be the glass, it might be a bit of the angle that the laser bounces not back to the sensor, but bounces away. And from about 80 meters out, we only see like at the back right corner. It's very, unreliable. So in conclusion, the sensor, it performs in compliance with the datasheet. I did a measurement, a maximum range of 150 meters with a high reflective object. It is less than 3 centimeters accurate at 50 meters. That's your measurement is not very reliable, but also trying to operate the sensor. I often had to restart my entire system just to get my sensor spinning. And it definitely had some reliability issues. Then the range is limited depending on the angle I put it, but also on the reflectivity of the object, the angle of the incidence. So if my panel is angled like this or angled like this, depending on the material capabilities, it's going to have a different measurement. And then most importantly, the humidity. I tested it in the LA desert, so I didn't have farming applications. Definitely in Western Europe, it rains a little bit more. The vertical resolution is limited for autonomous driving applications. And then proposals for future work. First of all, you need standardized test targets. I made my own test targets for just like a panel, 3 panels with a 10%, 50%, and 80% reflectivity. And even you have to put your test targets towards the thing you want to test. You need a more robust test rig. I put a little card and I could put my panels against it. I could connect it together, but you want that also standardized, so you don't have your measurement. So that was a bit the conclusion of my research itself. And then I would like to start a bit of an open discussion of will cheaper LiDARs, so it doesn't rain a lot there. It's also an American road. An American road is going to look different than a Chinese road or an Indonesian road or a French road. Or also driving behaviors are going to be different in India than they're going to be in Belgium. I think we all can agree on that. Then, everywhere in the world, they're not particularly locked to their geo-fenced areas. So I think one Waymo announced advantage, interesting things to discuss about. How do we actually measure the safety of autonomous driving systems? How do we measure efficiency of autonomous driving systems? If my car is stationary, I'm not going to crash. But do I get from A to B in an efficient way? That's also a question you can ask. And then will thermal sensors play for your attention? Feel free to ask me anything.
Thank you very much for your presentation, Thomas. I have a couple questions. In first, it's can you suggest a combination of sensors needed? Because something I like from your analysis is this easy to understand graph, spider graphs you call them. Is there any?
Well, I think you definitely need camera. Our entire road network is based on vision because it's developed for us, for our eyes. Radar for redundancy in tough humidity conditions, and ultrasonic for proximity. Those are the 3.
It makes sense to connect or disconnect sensors already installed in the car. Maybe you can have
I can imagine that, for example, in rain or in snow or in fog, you want to rely more on your radar than you do in perfect conditions. But yeah, that's a software question, I think.
and this regarding this sensor is if it is not economically viable, why are we
Cheap, and that the scale of the automotive market will drive the cost down. Why are we investing it? Because America.
Yeah.
I mean,
So I guess that they have potential enough to they have technical potential enough to.
that it has a little thing on the dashboard. Yeah, something like that,
Yeah.
maybe.
But yeah, my question is you have selected you have.
It's a bit dirt on the object you're measuring.
Yes. No, I was yeah, because for example, I do understand your answer right now because for example regarding rear cameras and things like that, there are nowadays a lot of cleaning systems for the camera.
Built in.
Yeah, and for example, the
Mhm.
are including cleaning systems for the camera. But I was trying to ask about
Yeah, the object
the
itself.
detected object.
That's why I went for a really dark paint because I just wanted to challenge the sensor,
Mhm.
see how absorb.
Presentation itself. If you can go please to slide 16. It's just it's not affecting the data you were presenting, but it's taking attention from the data you were presenting, and these are easy things that should be much more the same resolution and quality and so on. And 18, where they placed?
Yeah, there's definitely human error. The center of the measurements is
Should be at the same place. It's not.
It's roughly at the same place, but I couldn't control that as finely as I could do my measurement.
Okay.
So my error is going to be bigger than the error of the measurement.
Mhm.
Because it's about 1 or 2 centimeters sometimes.
For example, I would say that trying to be as precise as possible. It's really important because.
Yeah, but because my measurement was on both sides of my other measurements, I thought.
I do understand. And my last question is on slide 20. And what do you think about having a dynamic orientation as a function of speed? Because if I'm driving on a highway, no, you're talking about the angle and how the angle affects the
Well, first of all, I would say that this sensor doesn't have the vertical resolution for autonomous driving. That's why I actually did this because I was thinking, if you accelerate, your sensor is going to be a little bit like this. You can maybe have a cool control system that always makes sure your sensor is level, but have a better sensor, I would say. If you have a sensor with 128 layers,
I presume that it's you need more resolution in the near field, and if you are driving at high speed, you need more resolution on the far field.
So for example, it's hard with the spinning LiDAR systems, but for example, the Luminar LiDAR system is also a scanning system, but instead of their angular resolution, they can play with their vertical resolution. I saw them at the LA Auto Show, and they can play with their frame rates to give more layers. So for example, as soon as you start driving, you'll have better answers to your concerns. This sensor is quite limited.
Thank you very much for your answers.
Why you present artificial intelligence or why you present that? Because okay, I had in mind, maybe we'll use some specific algorithms to say, brakes. And
well, the reason I talked about that is because with artificial intelligence and deep neural small.
This is not artificial intelligence to react, because what I had in mind is to use LiDAR, to use an algorithm of artificial intelligence in order to make a good decision. I have time to use my brake and to react. If my speed is very high, the accuracy must be. So what could be interesting is or this is a good tool between 60 and 150. You understand what I want to say?
Sensor also has a reaction time.
Of course.
If you spin at 10 hertz, that means you only have a measurement every 0.1 seconds.
Mm.
That's also not that great.
Because in my point of view, even if this is expensive, you said $7,000, so expensive. I think that if the production start with large scale high, but the tool is very interesting from an accuracy and for reaction point of view, the price does not become a problem.
Very, very important. And then price doesn't matter because you only make one sensor, and if that costs $100,000, who cares? But I'm not gonna pay $10,000 more for my car to have 2 sensors on it.
Mm.
I think nobody would.
Okay, because you think that it does not replace all the other sensor, and because you think that it is not enough at this time performant
Mhm.
to replace all the sensor and to be enough reliable.
Yeah.
Say okay, even if it costs 10,000 euro, if you put in the car, you can sleep. You can sleep on the road. Okay, and so now if you can sleep on your car, maybe you are ready to pay.
Was it frequency modulated system? Yeah, there's work in that, and but not for the particular sensor I was working with.
And you also mentioned geofencing with the LiDAR testing.
Mhm.
Why did you do it, and why, or what is extra in the environment they use?
So yeah, they have a very high definition 3D map of the environment, and based on that map and their LiDAR system, they can localize themselves. So to a centimeter accurate position. For example, a car that only drives on GPS and camera can do that between it's maybe best case scenario 10 centimeters. It's 10 years here in Antwerp.
And why is that?
Because I don't think it scales that well. As maybe if you're maybe because I'm sustainable automotive engineering and I know some people, I might do a test drive somewhere left or right.
Mhm.
But as a consumer, I don't think that's here in the next 10 years.
Because of the price.
Because of the price and the efforts you need to put in to have a very high definition map of this environment. And Antwerp is not the same as Los Angeles, as a city to drive in. You have more bicyclists, pedestrians, trams, a lot of things that can happen that you need to train your system on.
But do you think it's a question of mapping?
Well, it's possible. It's possible to map, but it takes a lot of effort. So, and then you can do it maybe in Antwerp, but maybe not from Antwerp to a village
From
20
my-
kilometers farther.
Not an expert at all on the field, but I think it's the opposite to map in the sense that cities has always changing.
This is in your city, you have to update your entire map. So if the roundabout there was some traffic works since the last time I was here, yeah, I need to update my lab to be I need to update my map to be accurate with my LiDAR sensor, and that means you have to do it for the entire world. That's not feasible, I think.
Sensor fusion. I think it's possible. They also made Google Maps.
Of course, yeah, sure.
But yeah, all right, that was my question.
No, I think first my opinion and then my question. But I think it's typical that for people in technology that they overestimate the current possibilities, and then you started working on the LiDAR, and then you were disappointed because you saw that it's not that performant as you thought. On the other hand, we always underestimate the potential of time and the explosion of possibilities.
Yeah.
I have lots of colleagues who work on sustainable energy, and they said that wind and solar panels were not competitive to current generation of energy. Now, wind and solar is much cheaper than other means of electricity generation in just 5 years.
Yeah.
So don't underestimate the potential of the evolving technology. Although we are disappointed in what's possible right now, 10 years is a very long time in these kind of things.
I have to put an asterisk to it. I think on a lidar-based system, I
Yeah,
think
and-
I'm
Another thing I wanted to add is that but that's my opinion. I don't think anyone will buy a fully autonomous vehicle. You will not buy it. You will use it as a
yeah, so
robot
shared
taxi
as a
service.
mobility as
And
a
then
service.
I don't care if it was 3 times as expensive as a normal car to buy for the robot taxi company, because they will be able to exploit it 50% of the time, while our cars are only used 5% of it.
Yeah, of course, definitely.
But I also have a question.
Okay,
On slide number 20, you said that you are able to align your LiDAR with an accuracy of 1.5 degrees with the app you mentioned.
No, 0.1.
0.1 degree accuracy is 1.5 degrees, but we want to be sure that we will have this range of 150 meters at 1.5 degrees, or at 1 degree, or at...
Put your sensor higher?
Yeah, exactly, yeah. So in your measurement, you could have done so if really needed.
Yeah. Yes. Yeah, I based this.
But we're at 0. So in fact, the theoretical maximum range is not an issue here, because your accuracy was 0.1 degrees, and then your theoretical maximum is way above the yeah. And then slide number 16. Yeah. Can we actually compare those results, because the circumstances were totally different? No.
They were both indoor tests.
Okay, yeah, but do you know something about the temperature evolution of the left graph? Because you also stated here that it was in LA with a mild climate, etc. So you don't know.
No,
we're not sure if the left graph is also taken with the same.
It was. I did take the indoor test. So they did an indoor test and an outdoor test. Both are indoor tests.
Yeah, okay.
And then my lab was air conditioned, so it had 20 degrees Celsius. And then internally in the computing environment, I could see that my sensor heats up to about 45.
But still,
I don't know that for this sensor.
Yeah, but still we see that with the circumstances not that controllable as they might have been for the left graph, your right graph is better than the left graph.
Yes.
Yeah. Okay. That were all my questions.
Okay.
So thank you very much for.
Can you communicate?
Yeah,
Communicate
as Eve said, we cannot hear him, so
We can go.
We can call.
we can call him with David. We were going to try to call you if you want to give some input. I know you cannot give an answer, but
Ik heb zijn nummer. Ik heb zijn nummer niet.
maybe you have one or something.
Shall I just call?
Yeah, please.
Hi, Dr. Blackman. The academic board wanted to give you a quick call.
David, this is John from the University of Deusto. Thank you very much for attending the presentation, and we would like to give you the floor if you have any comments or questions for Tom.
Well, I tell you, the YouTube was super choppy. The first presenter, the one before Tone. I'm sorry, let me go back. Hello, everyone. Thank you very much for getting together and reviewing Tone's work. But it was somewhat very painful as far as watching, because the video signal was a little bit choppy, and the sound as well. So, but I think Tone did a good job and in Los Angeles. And what is important, and something I discussed with him a week ago, but he still didn't put it in the presentation, the amount of work it took to make that sensor work. So it actually took months to put all of the equipment together. So even though it might seem that it was an easy experimental work, in reality it was very difficult because we had to have two computers working together in order to run this LiDAR. And so it's not only the cost, but also the immense computing power that goes into running something like that. So I just wanted to make sure and highlight that it required a lot of work to just make things work. He contacted the manufacturer multiple times, got some guidance, and so on his own, he did a spectacular job in getting all of the software working. Multiple operating systems, as you probably know. So, while he was working on it, I'm not an expert in every automotive technology, so it was a great opportunity for me to learn more about LiDARs as well. So just by supervising him and working with him, but he did the major learning about this technology. And also he had a good exposure to automotive technologies in Los Angeles and other aspects. So when I asked him to present in class his work, first of all, we organized a lecture, and then we organized a lab where students helped him to do the measurements. So it was really good hands-on learning for a class of 20 students to work with LiDARs. Do you have any more specific questions on his performance?
No. We wanted to have your input, and with the broad explanation you've done on the work, the commission has enough input to come to a decision regarding the grade. Just to really thank you for supporting him and for hosting him in California. And yeah, thank you very much for collaborating with us in the project.
Oh yeah, no, it's a pleasure, having good students from your program coming over. And speaking of that, Texas is going to be coming just in a week.
Yeah.
So we're going to have a lunch next Monday.
Yeah.
So that's so I'm glad there is this continuation even here in Sweden. So very, very much looking forward working with you, and hopefully the program continues to survive in the future, or will have some future even in a modified form. But as you know, I'm ready to collaborate. Whatever you guys need, I will be happy to jump in.
Great. Thank you very much. Thank you very much, David.
Yeah, thank you. Yeah,
And
you can hang up.
yeah, thank you. Bye.
All right.
Bye.
Hope
Bye.
you hear a good decision soon. All right, bye.
Thank you. Bye. So, thank you very much. Maybe if you could please leave the room for 5 minutes. We will-
All the leaves, the baby, all the.
That's from,